Hello guys, so in this video we are going to see what is the fundamental matrix, and we are also going to derive the equations for the fundamental matrix. So let's see that. So in the previous video I told you that for a stereo problem we did two things. The first thing, that given a particular point in first image, so say take this point, where is the corresponding point in the second image? So we have to find out the corresponding point in the second image. So for stereo it was easy. The point in this image will have the same row in this image. So this point over here can be corresponding to a point on this line which is on the same row. So that was the first thing that we saw. And the second thing is this equation. So if we have these two things, that where a particular point is in the second image and the equation, then we are done. We'll be able to solve for any camera position the depth image. So in this video we are going to see the relation between a point in the first image and the corresponding line in the second image. So this is what we are going to see. So like given this kind of a scenario where the cameras are positioned without any constraints, suppose that I have a point over here and I want to find out that where does this point, where I have to search this point in this image. So instead of searching it everywhere in the 2D image, if I get a line uh, like this, say I get a line that tells me that you can search the corresponding point of this only on this line, so this point will lie only on this line, then that makes things easy for me, because I am reducing the two-dimensional ambiguity to a 1D ambiguity. So that is what we are going to see in this video, that how can we map one point to a line. Right. So finally we are going to dip into the epipolar geometry. So this is the sort of a general camera position of the two cameras. So here I have a camera which is centered at capital C over here. So this is one camera, and there is this other camera which is centered at C dash. So this is our 3D point that we are going to image, and this 3D points image on this camera is small x. So the camera coordinate for this 3D point for this camera is small x, and the camera coordinate for this same 3D point on this camera is x dash. So let us first go into Blender and get a 3D perspective of this scene, and we are going to see some more interesting things there. So let us first see that. So we are in Blender, and here you can see I have created a 3D scene of that image, the epipolar image that we saw. So over here, this point over here is nothing but C. So this is the camera center for this matrix. This point over here is C dash. This is the camera center for this camera, and this is our 3D image point. So I have here I have shown you a object. So currently we are just interested in this point, this point that we have, this point that we are interested in this point, right? So now if you see this configuration, if you see this view over here, so this ray that you see, this thing over here, is nothing but this point that we want. This is the 3D world point. I have joined this point to the camera center of this camera. So this here we have the camera center, and I have joined both of these points. So by this I get the image of this point over here on this camera. So this is the first thing. Similarly, we can do it for the second image. So this line over here is this 3D world connected to the camera center, and you get the image over here. Now this is the camera center 1, this is the camera center 2, C dash, this is C, this is C dash. So like this, by if we just connect these 3 points, this and this, we get a plane. So you can see this yellowish kind of a plane. This is what is known as a epipolar plane. This plane over here is known as an epipolar plane. So this is a very important plane. I'll tell you why. So coming back to our task, so what we wanted was, say we have one point selected on one image. So we have this point that is selected on this image, and say we don't know what is its corresponding point. We have to find out its corresponding point in this image. So how we'll do that? So given this point, what we can do is, we know that if we have a point on an image, we can find out the ray. So this ray can be found out, the equation of this ray can be found out. That is what we saw in the previous video, that given a 2D point, we can at least find out a ray which is passing through the 3D world coordinate and the camera center. So this ray can be found out. Now say I take a image of this ray on the second camera. So this line that you see over here, or in that matter this line that you see, this thing is nothing but the image of this ray, this hypothetical ray that we have drawn on this camera. So this line is a ray, is the image, this line is an image of the ray that we of this ray that we have formed. So now we know that the 3D point lies somewhere on this ray. We don't know where, but at least we know that it lies somewhere on this ray. So similarly, the image corresponding to this 3D point should also lie on this line, which is actually the image of this ray. So please understand this very nicely, that we have the image of this ray on this camera as this line, and the 3D point that we want, so the corresponding point to this in this image, will also lie somewhere in this ray. So like this, we'll be able to find out the line in which the point that is corresponding to this can lie. So that is the whole ideology. So a very basic thing to do is, we have seen that if we have a point, we have a camera point over here, we can find some other point by least squares which lies on this line. We can do that. We can find any point, say x dash. Let me draw. So say I can find out a point over here x dash which actually lies on this ray. Now if I just take, oops, let me draw a line, that's better. So if I just image this particular line on this camera, say I guess it lies somewhere over here. Now I have 2 points. Now once I just image this over here, so now I have 2 points. One is this point that I have got, that is the image of this some random point that I got which is on this line. So this is one thing that I got. The other thing is this point. What is that? So if you see this point over here, this point over here, so one is this point, the other is this point. So if you see this point over here, this point is nothing but the projection of the camera matrix of this camera center, I'm sorry, of this camera center. So if I project this camera center onto this image plane, I get this camera point, this point over here. And the other thing is, if I choose some point over here, say x dash, so that is what we can get it from least squares. So if I get some x dash on this line, and when I project this x dash onto this image, I will get the second point. Now given these 2 points, I can draw a line, and I can very well say that the point of interest, that is the point that corresponds to this point, lies on this line. So I hope this is clear, that how are we getting this line. So this is what is the goal of today's video. Given a particular point, we want to find out a particular line on the other image, which will tell me that the corresponding point on this image lies somewhere on this line, and this line is known as the epipolar line. So that is the first thing. The other thing that is important is that if you see this point over here, this 3D world point over here, so this is kind of variable. That means if I want to image this particular point, then you can see that the epipolar plane is like this. Now suppose that I want to image this point over here. So I want to image where is this point in this image, or this camera's image. So for that, what I'll have to do is, I'll have to rotate the epipolar plane and put it over there where I want to find out the point. So now I am imaging this particular point. So like this, you can see that for to image all of these points, I'll have to rotate the epipolar plane uh, consecutively, so that I can form an image over here and an image over here. So by this, you can see that the epipolar plane actually rotates according to the point that we want to image. So if we want to image this point, the epipolar plane will be like this. So this point that you see is variable. It depends on which point, which 3D point are you imaging. But if you see these two things, this center over here, this camera center over here, and this camera center over here, these both are fixed. This will never change, because they are with respect to the cameras. So once the cameras are fixed, this C and C dash will never change. So these are also fixed. So you can see that the epipolar plane actually rotates on this hinge that you see over here. So hence this hinge that you see over here is called a baseline, because any ray or any epipolar plane will always be hinging on this particular baseline. So this is also called as a epipole, because on this the whole epipolar plane is going to hinge. And what is this line? So if you see, this line is nothing but the joining both the centers of the cameras. So this, there was this C over here and C dash over here. So if I take a line that is joining both of these centers, then that gives me the baseline or the epipole. Other important thing, this thing that we noted over here, this point that is used for drawing this line. So this point over here is also known as the epipole, because it is this image, it is the image of the camera center of this camera onto this image plane. So I am seeing where is the center, the camera center of the other camera onto this camera. That is my that is also known as the epipole. So this is my epipole. So my epipole tells me, gives me the information about the epipolar line. So it is one point with which I can draw the epipolar line, and the other point comes from that other x dash the image of the x dash that we have got. So like this, for a particular point in one image, we get a epipolar line in the other image, in which we can find out the corresponding point. So this is the sort of a theory and a visualization of the epipolar geometry. Now let's go back. Right, so here you can see that this was the first camera with center C. This is the other camera with center C dash, and this is our epipolar plane. We have x over here, that is one point, and its corresponding point is over here. So if you see this ray, and if you take the image of this ray, you will see this line, and this line is called as the epipolar line. So you can see that over here. So this whole line is called as the epipolar line. This is our epipole or baseline, and for this image, this thing is the epipole. So that is the projection of the center, the camera center, onto this camera. So that is the center. Right, so this is basics of all the terminologies that we use in epipolar geometry. Now this is our task, mapping a point to a line. So given a point, some point, I want to find out what is its corresponding line. That's what we want. So every point in first image corresponds to a epipolar line in the second image. So every point in first image, say this, corresponds to a epipolar line in the second image. So this is the correspondence. So now considering an homography mapping between the two images. So consider that I have a plane over here. So this plane is not very important, but this is just for an explanation. So consider a point on this plane of pi. So there is this capital X, the 3D world point, on this plane pi. Now if I take its image in this, it will be small x, and its image on this is x dash. Now given an x dash and an e dash, suppose that we have an x dash and we have e dash. So what is e dash? E dash is that epipole. So given these 2 points, we can find out the line that we want, the epipolar line L dash. So we have seen in the basics video that if we have 2 points and we want to find a line passing through these points, we just take the cross product. So the cross product gives me the equation of the line. So the parameters, the ABC parameters of this line. So this is what we saw in the basics video. So now let us do some changes to this notation. So this is e dash cross x dash. Now it is seen that if so this is e dash, it will have e1, e2, e3. So this e dash over here, you can see that it is actually 2D. So it is on this 2D plane, but it has 3 coordinates, e1, e2 and e3. Why? Because this is in homogeneous system. So this is a homogeneous coordinate, analogous to x, y, w. So this is a homogeneous coordinate system. So e dash is a vector of three elements, and we can write a notation like this, ex, which is a skew symmetric matrix like this. So this is e1, e2, e3. We can place e1, e2, e3 such that we get a skew symmetric matrix like this. Now it is seen that if we just multiply this matrix with x dash, so that turns out to be the cross product. So instead of finding the cross product the conventional way, what we have done is we have made a matrix like this out of the e dash, and we multiply this matrix with x dash. So this gives me the cross product. Also, it is good to note that this skew symmetric matrix that you see over here actually has a determinant of 0. So this will be used further. So please note that this has a determinant of 0. Right, so coming back, so this thing over here can be written like this. So now E is a matrix and x dash is the point. So now x dash is equal to h pi into x. So we have some homography transform h pi by which we can come from here to here. So there is some homography transform that we have seen by which you can get x from x dash. So we can write x dash as h pi into x. So some homography 3x3 matrix into x will give me the x dash that is over here. So now just replacing these points. So instead of x dash I am writing h pi into x. Now this thing that we have over here, ex into h pi, this thing, if we just club it together, so that is what we call as a fundamental matrix. So fundamental matrix basically gives you a relation between the point and the line that you want. So we what did we want? We wanted that if there is a point over here, what is its corresponding epipolar line in the other image. So that is exactly what our fundamental matrix is giving. So you give me a point, you multiply that point with the fundamental matrix, you get the line in the other image that has this corresponding point x dash. So this is the importance of the fundamental matrix. Also, it is very important to note that fundamental matrix has a rank of 2. So this is a 3x3 matrix, but it has a rank of 2. Why it has a rank of 2? Because you can see fundamental matrix is actually made of this E and H pi. So H pi is a homography transformation matrix. So that will be a full rank matrix, 3 rank matrix. But this matrix over here, since we saw that it has a determinant of 0, so the maximum rank that this matrix can have is 2. So hence when you multiply two matrices, the rank is the minimum of 2. So hence F has a rank of 2. That is very important to note over here. Also, we don't know this h pi. So this h pi was actually only for explanation purpose, so that I can get a map between x and x dash. So that is just about h pi. But actually we don't know h pi. So it's okay even if we don't know h pi, we can still find out the fundamental matrix. We'll see that how in the next video. But for now, it is okay if we don't know the h pi. Also, if you see L dash over here, so L dash is this epipolar line. So if you see L dash, it is formed by 2 points, E dash and X dash, where E dash is this epipole, that is nothing but the image of the camera center of the other camera onto this image plane, that is E dash, and the other point is X dash. So now what is X dash? So X dash may be that point that we have got by least squares. So we had this camera and this point X. So by least squares we can get one point which is on this line, say this X, and when we project this X on onto this image over here, we'll get X dash. So getting these 2 points, we can draw a line which is our epipolar line. So we know that E dash and X dash. So this is E dash and the projection over here will be X dash. So small x dash. So this E dash and X dash are 2 points which make this line. So we can write it as a cross product over here. So L dash is the cross product of E dash and X dash. Again changing the notations. So over here changing this to a skew symmetric matrix, and X dash, so X dash is that point over here. So you can see that X dash can be formed like this. So this is our X. Now you first use the least squares and get a point which is on this ray, a 3D point which is on this ray, that is capital X. So you can do that by P plus X, where P plus is our least square estimate. So by P plus X, we are going from here to a point on this ray, and then when we project this point on this image plane, we will get the point, the X dash point. So please understand the projection matrix for this camera is capital P, and the projection matrix for this camera is P dash. So if you want to first inverse, that is you want to first from the 2D point get the 3D point, so for that you will need this P plus. So P plus is nothing but the pseudo inverse or the least square estimate of this P, so that gives you P plus. And P dash is nothing but once you have this 3D point, a 3D point on this line, you are projecting this 3D point on this image plane on the next camera, the second camera. So for that there is this P dash. So P dash is our projection matrix for this camera. So the parameters for this camera are all in dash. So that is what. So here you can see that this is again a map between L dash and X, which we saw earlier. So this is also L dash and X. So you can say that this thing in the middle is nothing but fundamental matrix, because that is also giving you an estimate between L dash and X. So one can also say that P dash P plus, this kind of a matrix, P dash P plus, this is nothing but our H pi matrix that we saw over here. You can see that the notations are quite similar. So if you compare this equation with this equation, you'll see that this is nothing but H pi. So like this we have understood what is the fundamental matrix. It is just the mapping or relation between a point in an image to its corresponding epipolar line in other image, and what is its equation, how is it derived. So we have seen that. So that's all for now. We'll further continue our discussion on epipolar geometry in our next video. So thank you so much for watching. Thank you.